to sticking with the Ernest Henry theme. And as Vlad mentioned, we have a number of collaborators looking at these large mineral systems in the Northwest. So Jeff Steadman from Codes again down at UTAS, take it away to talk about mineral chemistry rather than lithogeochem.
Cool. Can everybody see that?
Yes.
Good, 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 good. Let's go to presentation mode here real quick.
Perfect.
Excellent. Well, thank you, Helen, for the chance to give this presentation. I'll just be showing a little bit of the work I have been doing at Ernest Henry using Epidote trace element chemistry to try and track the signal of Ernest Henry. This is a project that, like Jonathan's, is funded by GSQ. And so I thank them for their support and also for the sampling assistance at the Brisbane drill core facility. So just real quick, I'll give a brief introduction to trace elements at Epidote, at least from the porphyry world. We'll look at Epidote at Ernest Henry and the results, and then maybe looking down the road at what we can do in addition to what I've already done. So in porphyry systems, Epidote shows coherent trace element behavior correlated with distance from a mineralizing center. And trace elements in Epidote also are correlated with fertility. That is, larger porphyry systems flux more metals. And so in the diagram on the right-hand side of the slide is antimony in Epidote over arsenic in Epidote from a recent paper in economic geology by Dave Cook et al. On Resolution, a porphyry system in Arizona. Distal to very large porphyry copper deposits, antimony and arsenic in Epidote can reach nearly 1,000 ppm, whereas proximal to either very large porphyry coppers or smalls, the antimony and arsenic content in Epidote drops off. There are reasons for that, which I will show here using this diagram. This is a schematic showing potassic zones, pyrite zones, and green rock zones in a typical porphyry system. So in the potassic core of a porphyry system, we're at high temperatures, we're depositing copper sulfides and gold. Epidote is not stable in this zone, but as you move out into the pyrite halo, Epidote does begin to form. However, arsenic and antimony and lead are still happiest in pyrite, and pyrite is available for them to go into, and so they go into the sulfide phase, and Epidote is left with the rare earth elements and yttrium. But in the green rock zone, temperature has dropped to rather moderate temperatures, and there isn't as much sulfide forming in this zone, so arsenic, antimony, and lead are substituting into Epidote. So that's a very quick run through Epidote trace element chemistry basics. Let's look at Epidote from Ernest Henry. So at EH, Ernest Henry does not have a lot of Epidote within the ore body. Epidote begins to pick up once you step outside the ore zone, but not very far outside the ore zone. And Epidote typically occurs with other calcium-bearing minerals in the assemblage, like actinolite, titanite, and calcite. But it also is present in sulfide-bearing assemblages, pyrite and chalcopyrite. So I'll just give you a couple of pictures here showing mineralogical relationships with Epidote. This is a sample. This is a 1-inch round polished block from EH242, a couple hundred meters outside the ore zone proper. This is a pyrite, chalcopyrite magnetite vein cutting through the host metavolcanic rock. And if we zoom in the yellow square there in the center, we see that there's a rather large pyrite crystal here that has inclusions of other minerals in the rim. And then outboard of that pyrite is some chalcopyrite, some magnetite, and actinolite and feldspar. So under SEM, we can see that it's actually epidote inclusions that are entrained in this pyrite grain. And again, there's your titanite, TTN, and actinolite, ACT. It's very hard to see, but I can just tell you that interstitial to some of the epidote inclusions in the pyrite grain is some chalcopyrite. So it's showcasing an interesting relationship between copper sulfide formation and epidote formation, at least in that sample. So in the trace element results that I'm going to show, I'm going to focus on 5 specific elements that I've listed there: arsenic, antimony, vanadium, bismuth, and manganese. And we'll look at how they vary compared to distance from the ore shell. And that's just on the right, a zoned allanite grain from one of the more distal drill holes in this sample set MMA3. So arsenic concentrations in epidote, there's 200 spot analyses represented here. 0 is in the ore, and we're up to about 4 kilometers away from the 0.5% copper equivalent shell. So you can see that close into the ore, we are at relatively low concentrations of arsenic. We pick up at about 750 or so meters outside that, but then we've got a big gap in sampling. Our next sample is about 2 kilometers out, is very low in arsenic. And then in our next group of samples, arsenic contents are starting to pick up again, close to the levels seen at about 700 meters out from the ore shell. Antimony likewise shows a similar relationship, although there is, generally speaking, more antimony even in the proximal samples as well as in those samples further out, sort of between 500 to 750 meters. Again, there is a distinct low in the 2 kilometer sample, and then it picks up again 3.5 to 4 kilometers out. Vanadium, variations on a theme, but it's still the basic story. Maybe a kind of double hump there in the vanadium concentrations in epidote. Getting up to very high vanadium concentrations, at least for epidote in the porphyry space. 1,000 ppm is very rare for epidote in porphyries. Bismuth, very low in, close to the ore breccia. A big kick at about 500 meters to 700 meters, and then it tapers off to about 3.5, and then we pick up again in that distal sample set. And then last but not least, manganese, it's got a similar sort of profile to bismuth. Very nice pronounced shoulder that tapers off at until about 3.5, 4 kilometers out. So what does Epidote say Ernest Henry smells like? There's a consistent pattern in these 5 elements, at least up to 1 kilometer away from the deposit. So very similar to what Vlad was just showing in the talk previous to mine. 1 kilometer out, we can be fairly confident about the Ernest Henry smell or the Ernest Henry signature. Beyond that, though, we are left guessing. So those increases that we're seeing in these trace elements 3.5 to 4 kilometers out from Ernest Henry, are they indicating the presence of another system? If we were to move another 750 meters or a kilometer further northeast from those holes, is there another system waiting to be drilled there? What would help is if we were able to infill sample within those 2 distinct gaps between the 750 meters out and 2 kilometers out, and then the 2 to 3 kilometers out. So that's just a very simple cartoon schematic. We've got the ore zone breccia here, K feldspar alteration halo in pink, and then the green is the sort of background metavolcanics. And with epidote, we see this shoulder effect in these 5 elements, and it remains to be seen what we can really say about the Ernest Henry signal once we get more samples from more drill holes out there. So that's all I've got.
Thanks, Jeff. That was awesome. and between you and Vlad, building a really awesome story for the Ernest Henry system. So we had a couple of questions in the chat, but then you answered the questions as the talk went along. So they've withdrawn the questions.
That's how to do it.
Well done. Good job.